I'm Michael. So I'm currently well, I recently just got my degree in May of 2017 in the Astronomy department, but I'm still doing post-baccalaureate research in the Geography department with the Hurricane Rainfall Group. And I learned R back in the beginning of 2017 when I took a GIS for R class. So this is sort of like some of the tips and tricks that I've learned, mostly through reading Stack Overflow questions over and over again. And they sort of gave some of these recommendations in terms of vectorization and common ways that they sort of promote beginners to not process their code. So basically, they just want you to take advantage of the power that R can give you by doing vectorized operations and just simple ways. And I'll just show you some simple ways to test your code, to test the speed of the code, as well as a few other ways to see where your scripts can be taking up a lot of the time. So okay, so we'll just start off by, so we only need 3 packages, so it's just the dplyr, plyr, and micro benchmark. So micro benchmark is one of the common tools that we use to test functions or scripts in R. So we'll just start by loading the libraries, all right, making sure those are all good. So I'll start by so I sort of put in a lengthy bit of comments in here, just sort of describing. So I'll start by giving sort of a background as to how R operates under the hood, because R is what we commonly call a high level or an interpreted language, where a lot of the operations are typically done, a lot of the behind the scenes work that the computer automatically does for you. So for instance, if we look at the simple expression of just assigning a variable, so we just assign x equals 1. So what you may not realize is that R is doing a lot of the work that we don't typically have to do in lower level languages such as C or C++. So for instance, R knows that X should be a variable. So it's going to start by putting or marking down that R should be getting some kind of assignment. And then we use the assignment operator, which is typically the left pointing arrow. So R is being told that X is going to get some kind of value stored to it. Okay, and the next part is, so we have this floating point number. So R behind the scenes is doing all of the work so basically it works to figure out that, first of all, this is a numeric class operator. So everything in R is a vector. So even though this is a single number, even though we typically think of maybe this as just a single number, it's actually a vector. Because if we look at the class of 1, it returns back a numeric vector. So everything that gets stored in R gets stored as a vector. So that's just like the standard storage unit for R. Whereas in other languages such as C, you have to specifically call out that 1 is going to be an integer, or that the X variable is going to be an integer. Whereas in R, it does all the behind the scenes work to tell that X is going to be this numeric class operator, and it's going to be specifically this value. So it eliminates a lot of the work. So R basically just takes care of a lot of the work. But as a result, it tends to get the reputation of being much more slower due to the fact that it does a lot of this work dynamically behind the scenes. So if we take another example and we want to reassign X to be the value, or to be a string of foo. So now what R has to do is figure out, okay, X is in storage. I have to remove the value that it previously had, which was 1 as a floating point number. So it has to erase that from memory. and then it has to figure out that so it realizes it's getting a new operator, and then it's going to take over the value to be a string now, or to be a character class operator. And it's not just as simple as just taking the whole string and putting it in storage. It has to remember it in a certain sequence. So it has to store each letter at a time. So it has to store F as a single unit as basically the first character of the string. And then it has to do O and then O again. And it has to remember that specific order. So and then it has to be able to convert all that behind the scenes in the computer to binary code, and then put that in memory. So it does a lot of the work. So it has to do a lot more overhaul or overhead work in making sure that it returns this exact sequence of FOO instead of like OFO or something. Whereas with other languages, you specifically tell it which variable, which operator. So basically, overall, this means that there's a lot more work that R has to do, and this makes it take a lot more time as a result. Whereas in like C++, you simply define the interval, or you can define an integer x by this simple expression of you have to specifically call x, and it has to be an integer class. But there can be several types of integers, so you have to basically there can be different types. So it can be a 32-bit, or it can be an 8-bit, and you have to take these things into consideration. So like in C, you have to worry about specifically how you store the data. Because if you store it as an integer, it's going to take up less memory than a floating point number typically. So like 8 bits versus 16 bits typically. So, but R eliminates all that stuff. So this is just sort of to give you a behind the scenes as to how R operates as a language. So there's certain trade-offs basically with using R versus lower level languages like C. So basically it does a lot of the overhead for you, but it takes a lot more processing to do so. All right, so that's basically, so this gets to the ultimate key difference between R and C++, which is the compilation stage. So basically, typically in C or C++, you write all of the code beforehand. So you define all of the variables, you write all the for loops that you're going to do to run whatever code it is, and then you have to physically compile the code. So basically, if there's any error in your code, you're going to find out during the compilation stage. So basically, you have to compile the code to for C or C++ before you can physically run the program. And then if you have any errors, it's going to throw up a bug, for instance. And then that's when you have to go back and fix it and recompile it. But it also has but doing this compilation has the advantage of making the code a lot quicker. Whereas R doesn't do any of that. It does all the compilation on the fly. So it's just doing all that stuff that I previously mentioned with assigning the variable and variable type automatically for you. And with stuff like assigning a variable, that's going to be instantaneous. So our computers are very fast, or are fast enough to be able to do those kind of operations on the fly now. Unlike back like 40 years ago when we didn't quite have the processing power to be able to do that on the fly. But yeah, but as technology has developed and computers became processing faster, we could design these more dynamic-based languages. Okay, so if we actually look closer at a lot of R functions, so like let's just take the R base function FFT. So if you were to typically write a function without the parentheses, you can sort of either find out the function. So basically it gives you a breakdown of what the function is. But what we actually can see is that it's making a simple call. So it's calling to a CFFT. So a lot of functions that you see in R are actually just code written in C, C++, or Fortran that just has a simple wrapper function around it, or an R wrapper function where it just simply, R can just make a simple call to that script, and it runs off of that C script. So this is one thing that makes a lot of libraries unique. So some libraries can typically run off of C or C++ code, and then they just use simple wrapper functions to make them usable for R. Where those libraries typically tend to be faster because they're using the faster lower level languages generally compared to R. Okay, so now that we sort of see where we can see differences in the speed of lower level languages being much faster because you build them up from the ground up versus R code, we can sort of look at the idea of vectorization and how R can still be used in an advantageous way to process our data very quickly, even though it might be higher level. Okay. So if we run, so here's the first example. So we have the Fourier, or the fast Fourier transform function FFT. So the first way that we could process it, so like say we have a vector of 1 through 3, and we want to process this arbitrary, this FFT function. We could simply just do it like where we take the whole vector and we just put it inside the function, and we can calculate it just like that. So this is the idea of a vectorized function, where we basically apply a function to the whole vector and apply the function to each of its elements once. So basically we just run the whole function one time, so to speak, on the whole vector. or there is the other way of where we do it element by element of the vector. So we could simply, in the second example, we could call the function for each element of the vector, so to speak. So basically we create a arbitrary vector y, and then we run a simple for loop going 1 to 3. We append each value to y, and then once y reaches the length of 3, then we can use the FFT function. So this is sort of the idea of, so this tends to be a much slower process of using, like typically this is how a lot of beginner programmers use for loops in R, is they try to do it element by element or calculating simple equations on a data frame row by row for values instead of trying to use it for the whole vector. So what we want to do is we want to be able to apply a lot of our code to be able to do it in the vectorized, this first format of where we just take the whole vector and apply our operations at once, because that just takes a lot less time. There's a lot less iterations. So overall, it makes our code a lot quicker. And so this sort of just gets at the idea that we just want to simply apply vectorization whenever possible, or when possible, but it doesn't necessarily mean vectorization is always necessary. For loops might be able to do it just fine depending on, as we'll see later, like the sample size. So like how many rows of data or how large our data sets are can make a big difference in whether we need to do vectorization as well. Okay, so, but yeah, so this ultimately gets at the idea of no matter what we do, even in C, we ultimately have to run for loops on data. So like C typically uses for loops just because that's the most fundamental way to do it, but they just do it in a much more, where they just call everything explicitly as they need it. Whereas in R, we can just apply the whole vector. Okay. Although there are some restrictions, as you know, that all of the vectors need to be one data type explicitly. So that can lead to some restrictions on what we can do to in terms of vectorized operations, knowing that all of them have to, knowing that every element of a vector has to be a numeric type or a character type. So basically the overall takeaway is that in R code, typically shorter is better. Typically shorter makes it more readable. It makes it overall more, typically if it's shorter, it's more vectorized and more optimized code in R. Whereas with C and lower level codes, you typically see this style of code where it's a lot more simpler operations or simpler statements, but there's lots of them to do the operation. So, and you'll sort of see that throughout the rest of this lesson. Okay, so now that we've moved through sort of the background and motivation for why we care about vectorization, maybe let's sort of get into the ways that we can sort of test our code. So the first method is the built-in method, which is called system.time. So in this first example, we'll take a look at the idea of pre-allocating our memory. So one thing that we might typically commonly want to do is have vectors where we want to grow them in some way. So we'll just take a simple look at the idea of appending to a vector or using the append function. So this first idea is that the type of vector that we use to append to. So the idea is basically we're going to run a system time function where we're going to test the time it takes to run this appends function. So basically I have this appends function here, which just simply takes a vector and some n number of iterations that we want to append. So basically n times that we want to append to this vector that we put in here. And it just appends that many times. So the first method that we're going to try to do is just simply initialize a empty data frame, which is a numeric vector, which we'll call numvec here. But in terms of pre-allocating our memory, if we know what the end size of our vector is supposed to be, or if we know that we're going to just do some simple operations like adding, multiplying, like two columns of a data frame to create a new column, we can simply just pre-allocate a vector of that known size. So in this case, we know that we want to append a million numbers to this vector. So we can simply create an initialized vector of 1,000,000 elements. by doing the replicate function or the rep function. So rep, and then we just simply put NAs to fill them. And the advantage of this is that with a known vector size, R knows where exactly to put that vector. Whereas with a numeric, whereas with the numvec, we have to recreate the object every time we run this for loop, or every time we append to the object. So we're gonna have to take, so if we have 1,000,000 iterations, by the time we get to 10,000 iterations, we're gonna have to copy that vector of 10,000 in order to add another element to it. So it takes input as a vector of 10,000 elements, and then it'll become a vector of 10,001. But as this gets bigger, it takes much and much more memory in your computer, and then as a result, it sort of builds up the amount of time it takes to process your functions, or to basically complete the function, so appending it. Okay, so we'll go ahead and run the appends function. So, and then there's the system time. So this is basically the base function for testing how long it takes to run a code, and this is in terms of seconds. So basically, the output is very simple. We simply just put in the function that we want. So appends, and then we just basically put in our function arguments. So then the vector that we want to append to, and then the number of iterations, so 1,000,000. And then we simply run this argument, and then we do the same thing for the known vector. Yeah, I didn't initialize that one. All right, so if we run both tests, you can already see a notable difference in the time. So basically, out of these 3 times that you want to look at, the user, the system, and the elapsed time, the user time is the one that's significant for system time. This is basically the time that it takes to run in seconds. So as you can see here, it's already a factor of 5 or 6 times faster by just simply doing something as simple as appending a function. Even though this is for 1,000,000 elements, you'll see for smaller sizes, it's much more smaller difference in time. So basically, this only saved you roughly like 37 milliseconds or something. However, if you're doing this operation over large data sets of hundreds of thousands of tables or whatever operations you may be doing, this small differences in time add up quickly. So it can build up to seconds or minutes added to your processing time, just by doing some simple operations like knowing the size of your vector that you want to grow upon beforehand. All right, so now, oh yeah, okay. So you see this is for very large operation, or for very large arrays, or for very large vectors of like 1,000,000. So now if we try to look at the same test of a smaller, so this is basically the same test, but with 10,000. Yeah.
Would you still be able to realize the time benefit if you declare as a numeric vector if you don't realize?
Yeah.
When you declare a numeric vector,
yeah.
Can you specify how long it is within that?
Well, I believe, yeah, there is a way to.
And would that allow you to still save time?
Yeah. You can declare, like, there is, I think, a vector function. Oh, okay. It'll produce that size. Yeah.
If you run it,
yeah.
so it will create it with 0 instead of 10. But sometimes you don't want it because if you have some error somewhere, you get zeros instead.
Yeah. So it using NA as the default is just nicer because it can be overtaken by anything, even though whether it's a string or a number. But but you have to be careful about which data types you use for sure. Because if there's somehow some overlap later down the road where you have some strings and some numeric character or some numeric elements in 2 vectors that you combine, it will overwrite one of them. So they will be either all translated to numeric or character vector. So you just have to take that into account. But yeah, you can declare any which way. So you can do this with data frames, with lists, with matrices, and it applies in the same fashion. So this is just the sort of basic example. Yeah. Yeah. So basically now we just run the same test that we did before, but with a much smaller size of 10,000. And we can see that this doesn't seem to make much difference. or it's on the order of a few milliseconds. But we'll see just down a bit how this can actually be noticeably different. So it's just a comparison, or just showing the fact that sample size or having smaller sizes dramatically decreases. So you need to have fairly large data sets before doing something as simple as append makes a big difference in terms of the operating time. Or doing some simple operations like for loop. So, okay, so now we'll look at a more complex or a more commonly used package of micro benchmark. So this is sort of the standard function that R people, or the R programmers use to compare functions. So like if they want to compare several types of functions, this is usually the go-to function. So essentially we're just going to use the same function as before, but we're going to basically have a for loop where we append 10,000 elements to it. All right, and then we're just going to sort of run the same test again, but we're going to do it with a micro benchmark now. So numeric, and this is just sort of to highlight how one is still considered a class of vector, which you'll see in a bit. So then we do the same thing with a known vector, applying the same known size of 10,000. And now here's the benchmarking stage. So we have the micro benchmark function here. So I just sort of declared the library and then the function for micro benchmark. So the arguments for micro benchmark are simply the argument, just like before, but you can list as many functions as you want. So we just use the vect append function, which I just ran, but we're just doing it for all three of the vectors that I just declared here: numvec, num, and knownvec. And then we can declare how many times that we want to run the function. So basically, we run each of these functions 100 times, and this will generate a statistical distribution of the performance of each of these functions. So if we run this function, it should take a few seconds. And if we look at the results, okay, so this one is a much more comprehensive table. Keep scrolling. But as you can see here, so it'll usually send out whatever units that it measures the test in. So we just have a typical statistical distribution value. So we have the minimum time that it took, the lower quartile. The ones that we typically want to look at are the mean and median. So the mean and median are the values that we typically look at for these tests. And we can still see here that even after running 100 tests, it's still roughly 4 times faster to create an append function, even though this is on the order of only 2,000, so basically 2 milliseconds difference for a vector appending a vector of 10,000 with where we declare the vector size beforehand. So it might not seem like much of a difference, but it is still noticeable. Yeah.
So to this number, you just use like a random number to create data?
Yeah. Essentially, this isn't sort of a random data. I just simply created a function where I'm appending. So I basically just have a function where I declare a list of some size n. I'm like, oh, oops, wrong one. Yeah, so I just simply run a for loop where I'm appending a empty vector with the index number itself. So from 1 to whatever n value I choose, so 10,000. So in this case, it's 10,000.
So that vector
we'll have 10,000 elements from
1, 2, 3, 4,
yeah.
5.
Yeah, so that's all that we're doing here. We're just appending the index number up until some n number that we declare.
I'm thinking about the simulation, data simulation. So
yeah.
Can we use the
micro benchmark?
Yes, can we use this for the data simulation?
Or
is this just the easy way to have the random number of data?
All that the micro benchmark function is doing is comparing 2 different functions, or in this case, maybe 3 different functions.
Yeah, it's just 2.
And running them a bunch of times and reporting how long it took to run them.
Yeah, so the next part that I was going to show is the plot that comes built in with micro benchmark. If I can get to it. Yeah, so there is a built-in plot. So this is going to be a violin plot where it plots the statistical distribution as a function of counts. So you'll see. All right. So as you can, so basically what this plot is showing each of the functions on the y-axis, as well as a distribution of the number of times that. How should I make this bigger?
It's Zoom. Because see Zoom.
Oh.
Right there, yep.
Oh yeah. Okay. Yeah. So simply, so this is for each of the functions. So this was for a known vec, and then these are just the two normal ones, and then the y-axis is the function of time. So basically, it's just showing you the statistical distribution. So as you can see, for the known vec, it has a much smaller interval time of roughly like 500 microseconds, and most of the tests seem to accumulate around there. Whereas these tests are pretty consistently slower, at probably around 2,000 microseconds. So this is just a quick plot to show you the difference in times. Yeah. Okay, so now we'll go ahead and look at a few different, so this is sort of an example of benchmarking and how to compare different different ways to append. So we're just going to look at three examples of three common ways that programmers typically use the append operation. So three ways to append numbers to a vector. So the first way here is probably the slow way. So we simply have a function here where we first declare the list, and then we have a for loop where we simply use the append function. So append is basically the slowest way that you could use to append objects, because it basically recreates the vector and then it appends the final number to it. So this is pretty much the slowest way that you could use to append numbers, and then this just appends it to a list, and then it just returns the value. So this is considered our super slow way to append, because it's basically using a for loop and then it's just using a notoriously slow function to do so. So a faster way to do this would be to use the index number itself to append. So we still have the for loop in this function, so we still declare an empty list. However, this time instead we use, so for list, you're all familiar with a list, right? Okay. So essentially all that we're doing here is this time we're speeding it up by using the index number to append it to basically say we're going to place it in this first spot. And we do so by declaring the length of the list previously, and then it just adds one to it. So it's basically saying append the next index number in this loop to the next element, the next empty slot. So this has the advantage of R doesn't have to figure out which spot to put in the list now. It's not physically copying, like from the previous function. It's not physically copying the whole vector and then having to figure out where to append it. So we tell it exactly where to append it, and this makes it somewhat faster. And then basically the next fastest way to do it is basically combine pre-allocation as well as defining specifically where in the vector we want to append it. So in this case, we define a list with an n size. Yeah, so the function is just basically putting in how many elements that we want to append to the final list. So in this case, we'll use 10,000 once we run the test. So we create a list of n size, and then we simply append that index number, or we pin the next number in the for loop to that specific spot in the list. So basically, this is typically the most optimized way to append objects to a list or any object, is to pre-allocate, or is to basically predetermine the size of the initial loop or the initial list, and then append it in a specific spot. All right. So once we run each of these functions, we'll define what n is. So in this case, we'll just use 10,000 again. And now in this case, we'll simply just use the micro benchmark again, where we have each of the functions, and then we just put the value of n that we want to use, and we're just going to do it 25 times because this function will take a little while to run. So it takes about like roughly 10 or 15 seconds. So that's another thing to consider too when it comes to testing code, is it worth trying to test the code? Because you might run into the problem where it's super slow, but you might not, or Yeah, where it's super slow, but the time that you try to spend trying to optimize it was not worth it. When you could have just ran those kind of slower code, or once you figured out what was wrong and tried to fix it, you didn't really save any time. You ended up wasting time. So that's another thing to consider as well. Is this worth doing? Do I have other stuff that I need to be worrying about in terms of research, like reading papers and just so it might sometimes be optimal to just run your code, or if you see that it's not going to make much of an improvement after doing a few tests, then it might be better to just run the code too. So that's always something that you have to keep in mind. So, and yeah, it saves a lot of frustration. So all right, so now we'll see the table and we'll see the difference that these three methods make. And you can see this is in microseconds, and the three methods that we've shown, it makes a dramatic difference even for 10,000 elements. Even though we ran this separate, we ran the test 25 times each. So now you'll really see it in the micro plot, or in the auto plot, yeah. Yeah, so this is the difference between the slow method, which is on the order of 10 to the 6 microseconds, and how much faster we can make the code just by simply doing a few small measures beforehand. We can improve our code by 3 orders of magnitude in time, from like 100,000 millisecond or microseconds to roughly 1,000 microseconds. Yeah, so all we did was simply optimize our first function to pre-allocate the space, as well as tell it the other trick was telling it in the vector, or like in that list, where to attach it. So like knowing the index position of where to append each of these values. So just by telling it that simply, instead of using this aggravatingly slow append function, which copies it each iteration. And then so the reason that it becomes so large is because the list keeps getting bigger and bigger and bigger, and every time you have to recopy this bigger and bigger function, it's basically exponentially increasing the amount of time you're processing as a result. So
I don't really understand. So for this function, we just want to check how fast or how slow of our code, right? And then if we want to improve it, so we have to do something else, like change our loop, or this function also can improve our code.
This is just sort of a simple example to show you how simply changing a very simple function. So like, this is just a very simple example of how changing a function, like an initial function, like appending objects to a list, and how we slowly optimized it by just doing a few simple tasks of pre-allocating. So it's going to vary depending on whatever operation you're trying to do, but basically trying to look for ways in which you use less memory, or you reduce the number of iterations you have to do on a code.
We're also going to show you towards the end of this presentation how you can have R take a look at a full script and tell you which functions in that script are taking a bunch of time. So that would kind of point you like where are parts of my code that are inefficient, and then you can maybe use some of these things to.
Okay. Yeah, we should clarify. Up until this point, we've just looked at it for individual functions. So everything that we've tried to test here so far is just for like comparing an individual function. So like if you defined a simple function to find the minimum value in a list of values or something, or the value closest to 0. So we're just trying to compare different ways to do that function. So this is very common, or for like if you have a specialized task, like there's more than one way to a solution. So this is just sort of an easy way to compare those different methods that you might come up with for trying to find a solution to simple tasks, such as appending objects to a list, or finding the minimum value in a vector of values or something, or like the value closest to 0. Yeah. Okay, so that's pretty much summarizes. So this micro benchmark package is useful for comparing simple functions, or just for comparing different functions and seeing which ones can run faster and slower. So yeah, and then this can show how optimizing your code, or just doing simple changes to your code, can make it much quicker. Okay, so now the next part is sort of something that many people might think about a lot, or they might try to implement a lot, but it sort of took me a while to sort of realize the power of just using a simple conditional statement within a vector to basically to solve for simple function or to solve for simple tasks. So like so I ultimately realized when I was doing answering this simple question that I was doing while doing my research one day, which was I basically had a large array or a large vector of angles between -360 and 360, and I was trying to think of a simple way to convert all of the numbers at once. So basically all the negative numbers, convert them to positive numbers by simply adding 360. So I wanted to basically make all the negative angles positive by adding 360. So I thought about it for a little while, and I tried by simply, just applying a for loop. So we have a simple example here where I've created a data frame of 10,000. So basically I've created a data frame of 3 columns with, so if we look at this data frame, it's just simply 3 columns with 10,000 different angles from -360 to 360. And what we want to do here is to simply convert all of these negative angles to positive angles. So we could do sort of a naive approach, which as a beginner program, I sort of thought, okay, I can do this each row by each column, which is the simplest method to do because I can just write a simple nested for loop to go through each row and each column and just look at each of those individual values. But as you can see, this code, it does the job, but it is pretty clunky. And then I simply applied the system time function to test how long this would take. And you can see it still gets the job done, but it takes a few seconds. So it's just a simple for loop where I just declare the number of rows in the data frame and then go through the number of columns and then just simply run a conditional statement where I look at each individual row and value to see if it's less than 0. And then if it is, then it will just simply add 360. If not, then it will just overlook it. So this is sort of the very clunky way to do it. So we want to be able to do it in a vectorized way. So we can simply do that in a few different ways, just using a simple conditional statement. And the way that we can do this is, so we just recreate the same data frame. So in this, so this is just using the base R way. So simply all we've done here is we've created a for loop where we go through each column individually, but we've simply just wrote a conditional statement where it looks at the specific row value and sees if it's less than 0. If it isn't, so it applies this condition to the whole array. So basically we're applying this conditional statement to the entire column of interest. So all 10,000 rows, it's going to analyze the statement at once. And then it's doing it for the J column. And then so basically all those values will become true if they're less than 0. And then it will add 360 to that. And then it will do that for all 3 columns. So this is a much more optimized way of just using a simple conditional statement. And then we put that in the row space. Right? My bad. All right, so we run the second test. And then the third method is which it can be just a simple dplyr method. Using the if-else function can be a lot nicer too. So basically you can sort of see how we've sort of made the code a lot easier to read with this dplyr function. So all we've done using dplyr is just write it in a mutate function. So we just go through each column and then write an if-else statement. So basically this is the condition. So with an if-else statement, you just simply type the condition, which is the column name, all the values in the column that are less than 0, and then we put the true value. So if it's true, then we add 360 to it, and then if it's false, then we just simply leave it as is. So basically this is just going through and doing the same exact thing, but as you can see, this is a lot nicer to read, it's a lot simpler in its format, and it is a lot quicker too. And this applies, well, we've applied it to all 3 columns at once. So now if we look at the results of the system test, we can clearly see that the test 1 is basically is much quicker. So we can see that So basically going through each of these tests, you can see that the for loop, trying to iterate over each element in each column, is a lot slower in general. And there's multiple different ways in which you can just apply a simple conditional statement within the data frame itself to make it faster. So, and then so this has the ultimate advantage of increasing the speed, and then as well as the readability of our code. Like even with this base R function, it's still kind of clunky to read since we have to write the name of the data frame multiple times in the column. So this is still kind of hard to read, but using dplyr has that advantage to be much more readable too. All right, and then sort of the last little bit of code is doing tracing or profiling. So this is where you can ultimately, so this is basically the main way that we use to test a script of code, and we see which function is running the slowest. So basically it'll give you a time. So basically so basically the function is called rproof. So basically it starts a profiling sequence where it will take random samples every 10 milliseconds in the code. So basically it will run through the whole function, whatever number of times so typically you'll write a for loop to run the code 1,000 times. And then it will just take a sample of which code or which individual function within our script is running. And then it will just do a simple count every 10 milliseconds. And then it will sort of give you a summary of what part of the code is taking the longest, or is being run the most at least. So simply what we have here is a random walk function. So simply a random walk is just basically, it's just a function where we just have a point jumping around 1,000 times, or for n number of times. So we'll just run it on this function. So here's the way in which we create the R profile. So this is the function to start the profiling session, which is rproof. And then the only output that we need is the file name. So we just basically create some file name which will be exported afterwards in the same folder that you're working with. So we simply start the session by hitting rproof. So as you can see up here, it started an R profiling session. So basically any code that you run from this point on, it will start recording it. And it will basically just take a sample count until it's done running, of course. So now we just have whatever code that we're going to run. In this case, we have the function that we just declared for random walk, and we're going to run it for 1,000 steps. And then we're going to do it we typically put them in a for loop and then run it for whatever amount of times that we want to run the function for. So in this case, we'll do it for 1,000 times. So it will just continue running the code. It's doing the calculations behind the scenes, doing the sampling. And then once the arrow pops back up in the console, now to end the sampling, we typically just write rproof and then put null inside, and that will end the session. And now there are a few different ways to look at the output of this of the profiling session. So this is sort of the base function way, or the base R way. So as you can see, this table, so it gives a few different tables. It gives the tables by self. So basically, this simply lists every function that was read during the profiling session, and it just gives you a simple amount of time that specific function ran. But it doesn't tell you where within the function it ran. So like sample int is within the sample function. So this just gives you a holistic report based on each individual function. So the by total, this tells you which part of the code actually ran the longest. And of course, for some reason, they show that the parent function. Yeah, this mouse is really sensitive. All right. Sure. And then, so you can see the parent function is what it's called. So the main function that was ran within that code that we did, that's going to appear the most time here. And as you can see, this isn't very intuitive because we don't know where the sample int function ran within the sample. So if we go back to the physical code for this function, we can see that sample int is nowhere in here. It's just sample numeric, exposition. So sample int is within it. So I managed to find a code on Stack Overflow for someone that's written a better summarization table. So this is for if you want to look at it. So basically I've provided the source function. So I just downloaded the function within the folder. So so source is what we can do to import another script and import all the functions that come with it. So we just run source and that R script, and that provides a new function called the profile table or prof table, and then we can run it with the same R profile file name that we gave it. And this is sort of a more intuitive table if it didn't write out so long. So basically what we have here is a table of the percent time. So it gives you the total percent of what a certain function ran, but it gives you the absolute path of which function ran. So it tells you where within the base function it ran. So basically the portion, so this function took 60% of the time, as we can see. So the sample int function, which is inside the sample. So basically, if we go back to the code, it's somewhere inside the sample function. So the sample int is, yeah. So it's inside this function where it's taking up most of the time for this particular function. So in that case, it might be kind of hard to figure out a way to optimize that unless you go and write your own sample function, for instance, or just try to find another way to rewrite the same random walk function. So this is just sort of a simple way to profile it. But there's a much more interactive way to do this as well, which we can show. Okay, so for this last example, we can simply, so this is just a simple matrix example. So I'm not sure what exactly this is doing. It's just running some matrix math, basically.
Basically creating a big data and then run a linear model and try to fit the linear model. So beta hat without the tool is where you use matrix algebra to fit it, and then beta hat tool is using the inbuilt LM functions by R to fit it. Yeah.
Mm-hmm. Yep. So what we can do, but we can simply just highlight this code. So there's a nice tool within our studio where we can just profile it directly. So we have this profile tab up here. So we can just simply highlight a certain chunk of code that we want, and we can start profiling. Okay, so this is a specific package called profile visualization. So this is an interactive tool that allows you to visually see where the majority of your code is. So it'll break down each subdirectory of functions, basically. So for the sample function, it will break down all the functions within the sample function and tells you which portion of it. Oh, wait. Yeah, because it had to install it. No, I installed the other package, it's fine. Okay. Maybe I just got to import it. Oh. Okay. It looks like that worked fine. So yeah, just install the prof.viz package and now it should work. Okay, and now then we can just simply do the profile and start profiling again. And then it will take a few seconds, but it will load a separate GUI or a separate window where you can see the profile of or the time spent for each part of your code.
Can you stop profiling?
Sure, it's probably just taking too long.
But instead you go to profile.
Oh, okay.
And profile selected lines.
Oh, I see. My bad. Yep. But that's pretty much the end of the lesson. So yeah. So overall, these are just some useful tips and tricks, or different ways you can look at different parts of your code, whether it's a function or looking at a whole part of your script to sort of break down what parts of your code are taking too long, and sort of just give you a little background as to what parts of your code might be running slower. So yeah, as you can see, so this is just a flame graph. This just shows you like every single test and where it peaked. However, if you go to this data tab, this is where it breaks down the whole code. So it orders it based on the time spent for most of the code. So you can see the coefficient function is where it spent most of its time. But if we break it down even further, we can see the LM function took all the time within the coef function. And within the LM function, you can even break it down further. So you could break it down as far as the functions build up. So you can see which parts of the code are taking the longest. So for the most part, basically calculating the coefficient is what's taking a good chunk of the time. And then, so this is like this is probably the main tool you would use in terms of trying to profile certain parts or for scripts of your code versus functions. So yeah, so that's pretty much it.
Any questions for Michael? Michael?
Cool. All right, thanks.
Hey guys, so we got about an hour to do just
some time.
Open Q&A. Got a question for a hand up. Anyway, who's got questions? One there, specific questions. What are you working on?
I'm going to